Okay, so welcome everybody to our colloquium today. And we will have Edouard Audit tell us about ISM, and Ralph will introduce him a little more, and we'll go from there.
Yes, that is a surprising task. Welcome also from my side to the exciting talk about interstellar turbulence and its applications to star formation. So, Edouard Audit got his PhD in 1979, did I remember?
97.
97, big difference, big difference. Big difference, I'm sorry. I'm sorry. From the Observatoire de Paris. And then he moved to Saclay, where he is ever since, so I have an easy task. And he is one of the specialists on modeling turbulence on supercomputers, but also with approaching the problem with analytic and theoretical models. And I'm looking forward to an exciting talk about this topic. And yes, the podium is yours.
Thank you very much, and it's a great pleasure to be here. So I will tell you a bit about interstellar turbulence and fragmentation of the interstellar medium. And so it's work which was done in Saclay with the following collaborator, which are mentioned here. So just some picture to start with. So that's a picture of interstellar flow. So it's flow within the galaxies. And so in dense region of the galaxies, and the scale is about a few tens of parsec, so basically 20, 30 parsecs here, or the cloud can be a bit larger. And so this is an image coming from air shell. So you see a projected density, and this is an image coming from a turbulent simulation. And so you see many filaments, many clumps forming. And so the idea is to try to understand the turbulence of this medium and to see how it will form dense clump, and then the dense clump will eventually form star. So I think this work has two aspects. One is more theoretical. It's to try to understand interstellar turbulence from a turbulence point of view. It's an interesting problem. And see also what are the consequences of this turbulence on star formation, which is of great importance for astrophysics. So I will be talking about H1. So that's neutral hydrogen. So it's an important component because it's about 50% of the interstellar medium. And it's important because the molecular clouds, so molecular clouds that form our H2, that's a molecular hydrogen. And they form from this H1 region by collapsing and getting denser. And that's in this molecular cloud that star form. So H1 cloud are really set up the initial condition for stellar formation. What we want to study is the formation of the cold structure, cold and dense structure that we will see, which are prestellar cores. And we also, as I say, understand the dynamical property of this flow. And we'll see that they are bistable, which means they have a hot phase and a cold phase. So I will detail that and want to see how the property of turbulence is affected by this two-phase flow. And finally, we'd like to compare with observation and see how good this theory compares to observation and what we can learn from the comparison between theory and observation. So just a slide I borrow from a team of Philippe André. So it's in French. So Philippe André is an observer, and he works on IMF. And so you observe here this dense, so that's observation, this dense condensation forming. And then he tried to measure the mass in this cloud, and he compares that to the initial mass function. And you can see that the pink curve here is the mass function. So that is the distribution, the number of objects in function of their mass. And so that's the mass function of stars, and that's the mass function of prestellar core. So it's this dense gas cloud here, and you can see that they are very similar. So the idea is that the gas fragment make dense cores, and that is the mass of this fragment which will determine the initial mass function. And so the initial mass function is the mass distribution of star, and it's a key ingredient in astrophysics, because a heavy star will eventually have very strong wind, will blow up, and so they will put back their material to the interstellar gas, and they will enrich the galaxy like that, while a small star will just cool down and remain quiet and not have any ejecta in the interstellar gas. So it's very important for the chemical and general evolution of the galaxy to know the proportion of dense star and the proportion of lighter star. So that's the astrophysical context. So from the physics, we have a rather simplified model. We have hydrodynamics with cooling and conduction. So the equations are here. So that's the conservation of mass, momentum, and energy. So this here is a heating and cooling function. So I will go back to that in detail. And the last term here is a conduction. So I will not talk more about it. We have done a lot of simulation with conduction. From a numerical point of view, it's quite demanding because most of the time you need to treat it implicitly, and the results are very similar whether or not you put conduction. So we have decided it was not worth to put it. So this model is very simplified, and there are many ingredients missing. Especially we have no gravity. So that's not so bad because we are at a scale where gravity is not very important. So gravity gather matter on large scale, and then in this cloud, gravity is not dominant, and then it becomes dominant again, where the dense core becomes gravitationally unstable and collapse to form stars. But before that, gravity is not dominant. We have actually no chemistry or equilibrium chemistry. So for many species, it's okay to consider equilibrium chemistry. It might be different. For example, H2, molecular hydrogen, the rate of formation and destruction can be comparable to the dynamical time scale. So some improvement could be done here. And we have a no magnetic field. So that's also an important assumption because it's probable that magnetic field could have an important impact on this turbulence, but it also makes the situation more complex and more difficult to understand. So now I will detail this heating and cooling function. So it was taken from the work of Wolfire. So we have cooling. Basically, we have process which heat up the gas and process which cool down the gas. And so this heating and cooling function describes the equilibrium between this kind of processing. So heating is mainly done by a photoelectric effect on grain, and we have a cooling by various lines. And so all these processes are taken at chemical equilibrium. And so if you add them up, it ends up to something like this. So in this plot here, you have the density of the interstellar medium. So from 10 to the minus 2 to 10 to the 6 particles per cubic centimeter. So it's rather low density. And here you have the pressure. So isotherms are lines which are about like this. And so this line here describes the equilibrium. So it means when you're along this line here, the heating and cooling process balance and to keep the gas at thermal equilibrium. When you are above this line, you're too hot. So these chemical processes are going to make the gas cool down to reach some point here. And when you are below this line here, the gas is going to be heated up, and you have a tendency to go back up there. And on the curve, again, you are at equilibrium. So it's a very distinct curve. And what is peculiar is this feature here, where you have a first bump here and another one there. And this is what allows the interstellar gas to be bistable. So if you take a medium at pressure equilibrium here, you see that you have 3 phases here which are possible and which can coexist because they are in pressure equilibrium. So a very low density and hot phase, one at medium density, and one at high density and cold phase. And so in principle, they can coexist. But if you look at this region here, and if you assume that you are always at a thermal equilibrium, you see that here the derivative of the pressure with respect to the density is negative. It means that this curve goes down here. So what it implies is if you have a little chunk of gas in this region, if it starts to collapse, it will get denser. And if it is denser, since this derivative is negative, the pressure will go down. So it means if it starts collapsing, its pressure goes down. Well, normally if you press on something, the pressure goes up. If the pressure goes down, it means so it will completely collapse. And the same way, if you expand it a bit, the pressure gets higher, and so it will expand. So it means that this phase here is not stable. So the gas here, it's an equilibrium, but it's unstable. So the gas will either go to the hot phase or to the cold phase, and it cannot exist in this phase here. Just one last thing which will be useful for the future. You can see that at high density here with this curve, so you get almost a straight line, and which corresponds to an adiabatic index of 0.7. So 1 would be exactly isothermal, and it's a bit less than 1. So it will be useful for later. So that's what describes the thermic of the gas. So now the different structures that we have. So we have hydrodynamics with this heating and cooling function. And so there's different lengths, characteristic scale of this system. So first you have the cooling length of, so WNM is a warm neutral medium. So it corresponds to, maybe I can, so here you have a WNM, so that's this warm neutral medium here. So it's about 1 or less particle per cubic centimeter and about 8,000 Kelvin. And here it's a CNM, cold neutral medium. So it's about 100 or more particle per cubic centimeter and around some tens of K, so 10, 20, 30 K. So in this WNM, the cooling length, so basically it's the time it takes for the gas to cool multiplied by the sound speed. So it's about 10 parsec. So it's the scale at which this gas is unstable and which can cool and form a structure by cooling. So it means if you want the gas to cool and form a dense structure, you need at least to have a scale of this size, 10 parsec. Then you can look at the size of the CNM structure that you form. So you cool this gas. So you take it from the hot phase, bringing to the cold phase. And so you can look at the size. So the density ratio is about 100. And so if you assume it's 1D, you get a size of 0.1 parsecs for the structure you form. And so that's already 2 orders of magnitude. Then you can look at the size of the thermal front separating the two phases. So you have a hot phase and a cold phase, and you have conduction. So you will have a small front, a thermal front between these two phases. So it's around 10 to the minus 3 parsecs. And you can look also this CNM structure. We'll see that they will move very quickly, and they can shock each other at supersonic speed. So you make very tiny shocks with very dense. And again, the length is about 10 to the minus 3 parsecs. So if we wanted to do everything, we would need a resolution about 10 to the 4, 10 to the 5, which is, of course, very difficult to achieve. Now, if we want to study turbulence, another point is what initial condition and what setup shall we take. So we want to resolve the small-scale cores, because that's what we are interested in. But also the turbulence is driven on large scale, and we need to resolve the cooling length. So we need a box that is big enough. And then also we need to maintain some turbulence. So we need some energy input to maintain the turbulence. So either you can do very large scale study of the warm neutral medium on scale like 100 parsec or more. So some people have done that, but then it's difficult to resolve the core. You can do small scale study, so about tens or few tens of parsec. And then you can do either forcing in real space, would mean you force the velocity in real space. I will show you that. Or you can do a study of turbulence, which could be scale-free on different scale, and you can force in a Fourier space or start from unstable gas. So there's many ways to do that. They are very different. I would say they all have something in common. It's that from the astrophysical point of view, they are all very unrealistic. And so it's a way to maintain turbulence, but it's very far from what happened in a real astrophysical situation. Because I would say in real life, so turbulence can come from a large-scale motion and differential rotation in the galaxy, so that's from large scale. And it can come also from a small-scale injection, from winds, from supernova explosion, from a feedback from small scales. So the way turbulence arises in astrophysical situation, it's much more complex. And we have to keep in mind that we have to try to look for something which I would say universal in turbulence and which do not depend on these conditions which are not very realistic. So the simulations I have to show you are done with forcing in real space. So we take a box of 20 parsec and we inject flow on two sides. So it's a cubic box, and the flow, it's a free boundary condition on the other side. And so that's the velocity along this side here. So the velocity is basically it rises, it has a plateau and it goes down. And on the plateau, it can have a various fluctuation. And we have a parameter which gives you the amplitude of the fluctuation. And the more the fluctuation, the higher is the velocity. I mean, the higher is the turbulence in the simulation. And we start from gas, which is here. So on the equilibrium curve, just before the peak here. So it's at 0.8 particle per cubic centimeter. So that's an example of a simulation. So flow comes in from the right and from the left. So we let the turbulence evolve, and we present all the results when we have reached statistical equilibrium. So it's still moving, of course. It's a turbulence simulation, but all the properties are, I mean, the statistical properties are constant. So what you see here in this region is the hot phase. And then I will detail you have shocks, and then the gas cools, and you form this very dense core here, which will eventually form stars later on. So we have done several simulations. So we have done 3 runs with B stable, so which means with this heating and cooling function, and always increasing the turbulence. We have done 1 run with isothermal, so as a reference, because many people use isothermal equation of state because it's easier. So with the intermediate turbulence, and 1 run is a polytropic equation of state. So with gamma equal 0.7, which corresponds to the high-end behavior of the heating and cooling function. So this is just to show you, yeah, it works, this simulation. So it's very dynamic. And so these have this clump forming, and they can eventually be destroyed by turbulence, and they evolve like that. And so we would like to now study the property of all these dense clumps which are forming. And so you can look, and so what you see here with detail, it's a shock forming. So basically you have 2 shocks, and the turbulent medium forming structure, which is in the middle of these 2 shocks. If now we look at things, so that's a cut. So here you have the incoming flow here, so it's rather laminar. And then basically on these blue sheets here, you have a shock. So the 2 flows are facing each other. It forms a shock. In the shock, the gas is heated. And then it cools down here, and it cools down, and it gets very dense. So it forms this red clump here. And in the middle, the flow becomes, you can see the line going around. So it becomes very, very turbulent. And it's another slice here. So you see the shock is basically here, and there's the gas cool and forms this clump here, which are here in red. So that's a bithermal flow with this clump. So we'll see that they are basically in equilibrium with the surrounding medium. And here, that's the same kind of picture, but for an isothermal flow. So you have the flow coming from the right and from the left. And what you see here is very different. It's a bow shock. So the isothermal flow collapses here, Gemek shock. And the structure here is formed by this bow shock here everywhere. So now if you look at the statistics of this flow, so that's the histogram of the flow in a density pressure plane. So here you see again the equilibrium curve. So we start with gas from here, and that's 2 isotherm. And the region between these 2 lines here and there represent unstable gas. So basically what happened is the gas is shocked, so it goes up here along the Hugoniot curve, and there it's out of equilibrium and it starts to cool, and it can sometimes stay in this unstable region or go down to the cold curve here and stop on this line and form a dense clump. So basically you can define warm gas, which is here, cold gas, which is here in this region, and gas here, which is kept, can be kept in an unstable region. And you can look at the fraction of these three components. And so A is the parameter that describe our level of turbulence. So we have a weakly turbulent, medium, and strong turbulence. And what you can see at least in these two is that the fraction of cold plus unstable gas is rather constant. And here it's still high, but it's a bit lower. And what you can see is the fraction of cold gas clearly diminishes when the turbulence increase. It means when you have a lot of turbulence, the gas transits to the unstable phase, but is not able to collapse. If you form cold structure, they are really torn apart by shear motion. They are dislocked, and it's very hard to form a dense structure if you have a lot of turbulence. So in order to form dense clump, which can then eventually form stars, you need to have a higher, not a too large density. Yes?
Are these mass fractions or volume fractions?
I think, no, it should be, no, it's mass fraction, sorry. So that's another isogram for isothermal flow. So this time in the density Mach. And so that's the gas which is injected. And for the turbulent part, it's rather spherical, and it expands around this average Mach. So here the Mach of a bit below 1, and with density going on both sides. So if you do the same plot for the B-stable run, so you have here the gas which is injected, and you have the dense phase here, the hot phase here, and the dense phase up there. So you clearly have a biphasic medium with one phase here and one phase there. And here I draw the line that proportional to the Mach proportional to rho to 1/2. So basically the two phases go through this line. So it means that, of course, you have a lot of motion and a lot of dispersion, but roughly you are, the two phases are, so this line corresponds to pressure equilibrium. So roughly this model of two phases in pressure equilibrium is on average correct. And then you have some, of course, a lot of dispersion due to the large motion. So then an interesting thing to look at is the density distribution function. So basically this diagram projected on the axis here. And so you can look at the PZ of density for isothermal flow, so which corresponds to gamma equals to 1. So the peak here is just spurious, is due to it's the density of the gas which is injected. And so otherwise you have this kind of shape for the PDF, and it can be fitted by a log normal. So it's work done by this author. So it can be fitted by a log normal shape, where the dispersion, the width, depends on the Mach number here. So the fit is very good in in this region here, where you have most of the mass. And then we can see that we still have significantly larger wings than predicted by the models. Then we can look at the PDF of other flows. So there was work by this author here, Passo and Vasquez Madeni. And they say that for gamma equals 1, you should get a log normal case. And in their model, it's a singular case. For gamma, you get a power law. For gamma larger than 1, you get a power law on the low density. And gamma smaller than 1, you get a power law at high density. So they did that from I would say, analytical argument and a 1D simulation. And so if you look at what we have for the PDF of the density for the polytropic flow, so that's a log normal fit, so it's very good in this region. And we see that the high density, it's well fitted by a power law, and so we recover their results. So for a polytropic index smaller than 1, we recover a power law at high density, and with an exponent which is close to what is predicted by theory. So that's the result for this simulation. And then if you look at the two-phase flow, so that's the gas injected, that's the the hot phase and the dense phase. And here we fit also, so it's this cut here is well fitted by a log normal law. So this is a bit of a surprise, but we see that the fit is quite good. And if you remember, the heating and cooling function at high density, it was very close to so it was almost a straight line with a slope of 0.7, so a polytropic index of 0.7. So we would expect more that we should get this kind of thing. If you say that we have a turbulence in the cold phase, then it has a cold phase by itself has a polytropic index of 0.7. So we should most likely get a power law here, as we see on this curve. And that's not what we get. We get something like that. So it might be that the cold phase, in fact, it's within the hot phase, and that these cold clumps are moving and are driven by the warm phase, and that's why we do not find this power law at high density. So an issue, you see what is a proper PDF to use when modeling molecular cloud. So it's an important theoretical question because when you study star formation analytically, most of the time you start with a density distribution, and then you try to infer from the density distribution what are the clumps and how are they going to form stars. And so you need to start with an initial density distribution. And we see that so log normal is a good choice because from a theoretical point of view, it's easy and it's tractable. But we see that depending on the physics, the PDF varies a lot, and it's not clear at all what should be used as a starting point of star formation, because you see that clearly this is much more complex than just log normal. So that was a property, generic property of the flow. Now we will look at properties of the dense structures that are formed in the flow. So this structure are just, we set up a density threshold, and we just look at the structure are defined by a connex region which are above a given threshold. So we can look that for the bistable flow. So here you have two curves, so that's for low resolution and higher resolution, so that's basically 500 cube and 1000 cube simulation, and that's the number of structure as a function of, the number of structure as a function of their mass. And we have done some kind of a Press and Schechter type model, so this is much used in cosmology. So you start with density fluctuation, and from this density fluctuation, you try to infer the number of structures. And from that, we find that in 3D, the number of structures will be proportional at high mass to the mass to this power, minus 1.77. And we assume that the density is Kolmogorov light and the per spectrum, and that the PDF is Gaussian. And we see that this minus 1.8 is quite a nice fit to the result we find for this bistable flow. And we did that also for the isothermal flow, and you see that still this is quite a good fit. And then we change the threshold, and we try the various things, and we always find that at high density we have this slope at minus 1.8 basically. So that's the isothermal flow, and we have been changing the threshold defined to as a threshold to define structures, and that's with a stronger turbulence. And so basically we always find that this slope is very robust, and in many situations, and either for the two-phase flow or for the isothermal flow. And one thing important to look at is that in both these flows you can define structure, and you define them as over density, and that's the zoom of the structure of the two-phase flow, and that's the zoom of the structure on the isothermal flow. And you see that, first of all, they look very different, but also physically they are extremely different. And so you can define structure in both flow, and they are both structure in the density field, but they are extremely different from a physical point of view, because here they are formed because of the heating and cooling function, and roughly they are in thermal equilibrium with the surrounding. So here it's higher density, but it's cold. Here it's lower density, but it's hot. So roughly it's in thermal equilibrium. So these are long-lived structure. And in the movie I showed you, you can follow the structure, and they really exist, and they have a long lifetime, and they can move around and eventually collapse to form star. While if you have a isothermal equation of state, so basically the density, the pressure is proportional to the density. So if you have a high pressure here, a high density, it means you have a higher pressure than here. So it means that this structure cannot be, of course, in a pressure equilibrium with the surrounding. And in fact, what you have here is more like a shock, and matter is actually moving through this shock. And so this is not a long-lived structure, and you don't have a bunch of matter which is coherent and is moving together. And so when you have a static view, you can define density structure in both cases, but in fact the structure you find in isothermal simulation are very different, and probably, in my opinion, it's more difficult to form stars. So now we can look at more property of this clump. And so one thing common is to look at the relation between their size and their mass. And so that's all the clumps that we find here in a bistable flow. And the mass is roughly proportional to the size to the power 2.5. And we can do that in the isothermal run. And we find the same scaling relation, but don't forget what I said about the difference of the structure. But nevertheless, from a statistical point of view, they are very similar, which an exposant which is a bit lower. We can also look at the velocity dispersion. So that's for the bistable flow. And we find that the velocity dispersion scale like the size to the power 1/2. And for the isothermal structure, so the dispersion is quite large, but the fit are rather similar, and they do not depend so much on the size. We can see, so that's the same thing for 3 different thresholds. So that's the different fit for the velocity dispersion. And for isothermal run, the index here is independent of the threshold we use to define the structure. While for the bithermal run, you see that the exponent is changing and is going down as we go to the denser part of the structure. And for CO clump, so CO clump would be even further. They are a very dense clump. It would be more like in the regime of 1,000 particles per cubic centimeter. And we find this kind of velocity dispersion, which is rather coherent with what we have here. So now we can try to compare to observation. So that's the mass spectrum here, so of clumps. So they have also a slope, which is minus 1.8 also. And the relation between the size and the velocity dispersion, they find something which is similar for CO clumps, so that's for dense region. And other people have been looking at that. So Falgaron, so they also find something between 2 and 2.3. And other authors also 2.3. So basically, the slope is around between 2 and 2.3. So it's quite coherent to what we have. So just conclusion for this part. So one thing that the 2 phases are very mixed, tightly interwoven, and there's a lot of gas which remain in the unstable phase due to turbulence. So this can have a consequence from an observational point of view, because when you make observation, and when from observation you try to infer quantities such as density, temperature, things like that, you can have tracers, and often you assume that the gas is in thermal equilibrium, and it's a significant fraction of the gas can be outside of thermal equilibrium if you have a large turbulence. Another point that I think the PDF of the density is strongly depends on the thermal property of the gas. And so it's a question what is a good description of the distribution of density in this region. Another point that the structure formed in isothermal and in disturbance flow have very similar properties. And if you look at them from a statistical point of view, they are very similar. And all is consistent with observation. But they are also very different. And the physical nature of the structure is very different. Another thing that the property of turbulence is strongly affected by thermal instability. And then another question is, how does all this depend on the forcing? So all these results are for conversion flow, and it would be important to know whether or not that depend on the forcing, and in all of this is only for this kind of forcing or is more generic. So to look at that, we have done some simulation in Fourier space. So it's the same kind of simulation, but this time we force in Fourier space, and we inject energy in Fourier space on the large mode. And so the simulation are its periodic boundary condition on all sides, and we inject energy in the low frequency mode, the larger scale, and then it just makes a cascade and goes down to the smaller scale. And so we have done a series of runs, so it's ongoing work. And we vary the density, basically from 0.5 to 5 particles per cubic centimeter. And we vary a parameter called Xi, so it's the ratio of a compressible versus solenoidal mode. So when Xi is 0, it's a purely compressible forcing, so only a divergence field. And when Xi is 1, it's a purely rotational field of the forcing. So one thing to note is that in the previous simulation, so you had forcing in a real space and then a free flow on the outside, so the density in the box could adapt itself to what it should be. While when you do that, you have forcing in Fourier space, so it might be, I would say, cleaner from the point of view of turbulence, but then the density in the box is fixed. And since you have this cooling and heating function, so you have a lot of constraints because you cannot adapt, the density cannot adapt in the box. So we did a series of simulations varying these two parameters. And here you see the fraction of a cold gas. So that's the density going from 1/2 to 5. And that's this zeta parameter. And you can see that the more the density is higher, the more you form dense gas. And also that if you have a high zeta, it's favorable to maintain gas in the unstable phase. Of cold gas. So that's the fraction of unstable gas. We have a peak in this region, and that's the fraction of cold plus unstable gas, which seems to depend mainly on the density. So we can see that in this region, you can only to form structure, you need to be, of course, it's easier to form structure in dense gas, but also you need not to have enough compression and not too much solenoidal forcing. Okay. And if you have too much solenoidal forcing, then you have a lot of shearing motion, which do not compress the gas, and then it becomes impossible to form structures. So when you have structures, we'll also look at the scaling relation. So basically the distribution of mass, the distribution of, the relation between the size and the mass, and the relation between the size and the velocity dispersion. And we find things which are similar. So basically between around 2 for the scaling in mass. And if you look at all the simulation we have done, so we have about 25 simulations, and the scaling exponent is always between 2 and 2.5, which is quite consistent with observation. And for the velocity dispersion, here we find between 0.5 and 0.8, so the scatter is a bit wider, and it's still roughly consistent with observation. Observation would be more on this side, more 0.5, and 0.8 might be a bit too large. And basically, in observation, so it's the dispersion is more on CO clump, so it's on the very dense part of this observation. Okay, so to finish, I just would like to present a recent work. So now we have been interesting to look at this region and how they, so it's this turbulence simulation, how they interact when they meet the ionization front. So you have this turbulent medium, you have this structure, dense clump which form, and then they will eventually form star, and then this star which will have a ionization, emit ionization radiation, and which will create a ionization bubble inside this simulation. So we wanted to study that. So we took a piece of the previous simulation I showed you, and we casted some ionization flux from this side here to see how it would react. So I don't know if that's going to be working. Yeah, so you have the ionization fronts coming from here. So it's ionizing the gas, and here you have a separation between the hot ionized gas in the bubble and the rest of the gas here. And you form pillars here and structure. So the idea was to study, in fine, would be to study in this region the structures that form and see that if you get more clumps and if you enhance star formation, or if on the contrary you destroy the clump and reduce the star formation. And you see that at the limit between the hot and cold gas, you create some pillars. And so just to show you some pictures. So basically what we want to study is the H2 region. So you have the ionizing source here. So basically massive stars, O or OB stars. And you have the surrounding gas here, and you form pillars and clumps at the edge between the cloud and the ionizing bubble, which is here. So that's a different view of this situation, mainly from air shell data. So the context is that in this star forming, we want to see if in this H2 region stars is triggered, and how do these pillars and globules form, and want to see, and it's a difficult question, whether a star formation is enhanced or reduced by this radiation. And on a galactic scale, we want to see how massive stars inject their energy into the molecular cloud, because this ionization front is also potentially a source of turbulence. And then, finally, an important question would be how is the star formation regulated? Because mainly this large cloud I've shown you before, only a few percent, maybe 10% of the mass is converted into star. So it means that at some point the collapse and the formation of star is stopped, and that not all the gas is converted into star. So basically you have the cloud here, you have the H2 region, which is ionizing the gas, so the pressure gets higher, and you have a bubble which grows. And inside the bubble, the ionization is 1, and the temperature about 8,000 degrees. And here the gas is compressed, so you have a compressed shell. And outside, the ionization fraction is close to 0, and you have 20K. So here is the interstellar cloud we have been talking before, and you have a dense shell between here. So that kind of a collect and collapse scenario, which was proposed by Emergreen and Lada. And the idea would be, in this region here, can you form more star or not? And you have other model which has been proposed. For example, a radiation-driven implosion here, where you have only one clump and which is irradiated and is made to collapse only by a radiative ablation on the side, or a more turbulent approach similar to ours, which has been proposed by this author here. So just a quick look. So we have just done idealized setups where you just look at one perturbation and see how it evolves, one density fluctuation, how it evolves under the radiative flux, and one more turbulent situation. So we have out of equilibrium ionization, but I will skip that. And just to look at here, so we have done interface modulation. So ionization radiation comes from the top and arrive here on the density modulation. And we have kept the same height, but made the density modulation more and more narrow. And this is what happens here. So you see that the thing is collapsing on itself, and it's digging on the side here, and it will eventually make a pillar with two holes here. And here you have higher pressure gas, which push the matter towards the base of the pillar. And so the shock is concave, it can collapse of itself to form a pillar. And if you look at what happens here, so that was with a wide modulation. So if the modulation is wide, it's not enough to curve the shock, and so the shock are not bended enough to collapse on themselves, and so they don't form a head of the pillar, and basically everything is pushed forward, and you form a condensation mainly on the shell. And if the condensation is narrow, yes, then you can bend the shock and form a very long pillar here, and with a velocity gradient from the bottom to the edge here. So we can look that these pillars, they are growing in size, so that's the width. And here you don't form a pillar, you just form a condensation. And they all have basically the same mass accretion rate. It means their mass grow with time. So an interesting thing in this scenario, so that's a density pressure diagram, is that you can form very dense structure, and that's the density threshold of the collect and collapse scenario. And here you can reach more higher density. It means you can form structures which are much denser and much more able to eventually form star and collapse. And also some observation. When you look at this forming pillar, so you have two shocks here and there which are collapsing. And if you look at them in velocity, you see a double wing, which is typical of this, one wing coming from this side, and of course the other wing coming from this side. And when everything is collapsed, you get a single peaks for the pillar, because everything is together in the middle. And we did the same for turbulence simulation. So against the ionizing flux from the top. And you can see, so here you have a turbulence at Mach 1, and here at Mach 4. And so here the ramp pressure is much smaller, the turbulent pressure, than the pressure of the ionized gas. And here it's much higher. And you can see that when the ramp pressure, the turbulent pressure is high, you can have some matter going into, dense matter going into the ionized region, which is stopped. While here the matter is pushed and is not, no cold gas is able to go into the matter. And just to show that we find the same mechanism to form pillar here in the turbulence simulation. And just to conclude, I can show you some observation where we have seen, so observe pillar and globules. And we can see that the globules and the pillar have some good characteristic, which means we have a velocity gradient along the length of the pillar. And we see that we have globules in the cold gas, which have a velocity shift towards the shell, which means that they probably come from turbulent gas, which has been injected into the hot region. And okay, we'll stop here. Thank you.
So thank you for this very interesting work, and you trying to explain the observation. It's really exciting. Yeah. Are there any questions? Sorry,
I have a question to the first part of your work, where you showed the different turbulent calculations, and you changed essentially the equation state gamma.
Yes.
It looked to me like the clumps you see are all extremely low mass, typically of order of a few Jupiter masses, while if I look at the CO observations in nearby molecular clouds, usually the masses are much larger.
The mass is here, so it's 10 to the minus 1 to 10 to the minus 3 solar mass, basically.
Yes, but that is much smaller than any pre-stellar core that could form a star, typically has. And if I look at larger molecular cloud structure observations, typically the clouds have one solar mass upwards.
I think
how you can get big structures in these calculations.
I think for this mass, so we have two cutoff here, and so the cutoff on small scale is due to a lack of resolution, and on large scale is because it's more rare event and we would need a larger box.
But your box is already 20 parsecs across, right?
Yeah, but it's 20 parsec, but it's filled initially with WNM, so it's a very low density. So I think that's probably not enough, the mass reservoir is not enough to form a very dense core.
But wouldn't you say the total mass is order of a few hundred solar masses?
The total mass?
Isn't this just a typical size you expect from the thermal instability?
Yeah, but it's complicated because the thermal instability has no, I mean, you can fragment at any scale, and then the scale length, we thought it would be fixed by the conduction, and that basically a small structure would be evaporated by conduction. But in fact, when we introduce conduction, we find almost no difference, because actually the dense structure have a heat capacity which is much greater than the low density gas, and basically the low density gas is not really, I mean, the heat from the low density gas is not really able to penetrate the dense core, and we find a very few difference when we introduce heat conduction. But
I have a question to the structure of turbulence. You have nicely demonstrated that the statistical properties of the last relation so are very similar for your two-phase medium and for the thermal case. But the space structure is completely different. Is there any measure, statistical measure, to distinguish that?
To distinguish
between the two different cases?
Well, the density PDF, of course, are very different. And then I have not time to show, we have done a spectra of turbulence, and those are quite, it depends how well you could measure them, but they are very, very similar in both cases. So I think the main difference between isothermal and bistable would be the density distribution, because it's clearly you have one peak for isothermal, and with the width which is determined by the Mach number, while in bistable flow you have two peaks in the density distribution.
Then can you explain again or at all how the PDF is connected to this mass?
So it's connected to what, sorry?
The connection between the PDF of the densities and this mass power law or the mass distribution of the plants.
Oh, it's a bit complex. Basically, what people, when you want to try to have some analytical model to determine this mass function here. So basically what you say is that you start from a given density field. So the density field basically is given by a PDF and some correlation. And then you try to do a simple physical model to say how this mass distribution will form structures. And so you can say it's going to be done by gravity, by pressure. So you have a model. So you start from here, and then you try to have this physical model to infer what will be the structure form. So, and there are many. So we have done one, Bell and Chabry have done. You have various model, but they all start with the starting point is always the distribution of the density. And for example, in the Pache-Cherchta model, you smooth the field on a given length, which gives you a certain mass. And then you have a criteria to say whether or not the mass inside this volume will become a structure. So it can be that the cooling time is small enough, or that it is gravitationally unstable. And then you can statistically infer the number of structures that will be formed. And what is, most of the models, they recover the same slope, minus 1.8 or something very close to that. And even if they are based on very different physical arguments, they always end up having this very steep slope, a bit less of -2.
Can I maybe, before I get to the next question, ask if anybody, if the student has a question that they want to ask? You know, we usually have this policy that you get the first question that I completely forgot to take. If not, then...
Okay, I wanted to ask you, when you started saying that you form clouds out of a warm medium, hydrogen, H1, etc. Then you said that you expected from your calculations that if you increase the external turbulence, that you have less and less gas in stable regions, but rather you increase this unstable gas regions. Is there any, first of all, is there any asymptotic case? Would you expect that if you increase this turbulence or the ambient supernova, let's say, more and more that you cannot form clouds at all?
Oh, yeah.
Is there always a residual?
No. Well, I would say, for example, in this, in the other simulation, not this one, but in this simulation, in Fourier space, there is a lot of situations where you do not form any structure. The gas is not able to transit to the cold region because you have, if you put a lot of solenoidal mode and a density around 2, basically you don't form any structure.
And to what kind of astrophysical environments would that apply? For example, would you expect in an OB association to have this effect, that you don't form any clouds anymore, so the thing would essentially die out?
Well, the point is, when you have OB, so you form, basically you have your OB association, you form H2 region, and then you inject energy, but you also, so that's bad to form structure, but you also compress the gas, and which that is good to form structures. And so at that time, I wouldn't be able, I think nobody can answer whether or not it would enhance or diminish star formation. What we know is that molecular clouds, they do not live so long. And at the end, star formation is able to totally evaporate the cloud. So at some point, we know that it will stop star formation because the cloud will be disrupted. But if you have one OB association, you also have probably a second generation of star forming in this dense shell around it. Yeah.
Okay, are there any more questions?
If you would try to simulate higher density ISM region and increase the density in your box considerably,
Yeah.
would you still get this bistable behavior?
No, actually, so, and I think that's the answer to your question also. We have a low mass because it's low density. Because in the molecular cloud, you're more around a few hundred. No, because then you're always on the, if you start with high density, you are always on the, wait, at the beginning, on the cold place of, yeah, if you start, so see the density here is 10, so if you start with gas at around between, I would say above 100, you are always in this region. And then you don't have this bistable phase. That's why people often do a simulation with an isothermal gas, which represent maybe this end of the heating and cooling function.
Okay, so the properties would be more similar to the isothermal phase?
Yes, probably. Or polytropic, I would say. Yeah.
I think can I just refer all the other questions because we're starting to run low on time to the dinner. So feel free to come and join us for dinner, and let's thank our speaker again.
Okay, thank you.